Welcome to Cubing Combinatorics, episode 2. On this episode, I will be focusing on orientation of pieces. As I'm sure all of you know, corners can be in one of 3 different orientations. Edges can be in one of 2. Or so, what's a good way to represent this? Let's say we want to work out the number of OLL cases on a 2x2. Now, any one of these corners can be in one of 3 distinct orientations. And we're only worried about these 4 corners. Now, we could just go through and say, oh, well, 1 position, 2 positions, 3 positions. 1 position, 2 positions, 3 positions, and so on. So you might think, well, if we have 4 different corners and they can be in one of 3 different orientations, well, that will give us 12 cases. However, as I'm sure you're aware, that's not only correct, the logic in it is also flawed. So, let's say we represent each one of these 3 different orientations with an individual playing card. So let's say the diamonds will be this orientation, the hearts will be a twisted orientation, and the clubs will be the last twisted orientation. So, say we want to find, in a similar way to last time, say we wanted to find all the OLL cases, well, then we can use 4 of this different model. So each one of these different numbers can represent an individual piece. So, let's simplify the problem again. We'll go down to 1 piece. By itself, how many different orientations could 1 piece be in? As we've just established, there's 3 different orientations it could be in, represented here by the diamonds, the hearts, and the clubs. So now say we have 2 different orientations. Well, one way to count this is if we start with diamonds, well then we could put 2 diamonds together. Or we could put a diamond and a heart together. Or we could put a diamond and some clubs together. And if we repeat the process again, let's say we use the ace of hearts this time. Well, then we can have the 2 of clubs, 2 of hearts, and 2 of diamonds. And one more time, with the 2 of clubs, then we have the diamonds, hearts, and clubs again. So, that gives us a total of 9 different permutations, 9 different orientations any 2 corners could be in. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different orientations for 2 corners. Now, if we extend it to 3 different pieces, I'm going to give you a second to guess how many orientations we could have with 3 different pieces. So, we could count it all over again, but that's long and inefficient and boring. So, what have we really been doing? We've been taking each member of the first set and then saying, well, you can have 3 different here. So if we treat that as one set together and say there are 9 different variations of these 2 cards, then we can just multiply by 3 again, because there's 3 different sets for each of these 9 different positions, which gives us a total of 27. So, that gives us 27 different possibilities for 3 corners. Which brings us back to our final state, 4 different corners, 4 different positions. Again, see if you can guess how many, and then I'll go through them. So, we've got 3 first, 9 for the second, 27 for the third, and as I'm sure you've guessed by now, we just multiply by 3 again, and that gives us 81 different possibilities. So if you have 3 objects in each set, and someone asks you, how many different combinations can you have of those sets? The answer would be 3 to the 3 to the 3 times 3. So if you have 3 times 3 times 3 times 3, that will give you 81 different combinations. However, I'm sure you're going to say now, there aren't 81 different combinations for your corners. There's nowhere near 81 different OLLs, otherwise no one would learn OLL for 2x2. Or 3x3 for that matter. So, how do we get rid of those positions? As I'm sure you realise by now, I've not been taking into account positions which aren't possible. I've been saying, yeah, any corner twist is possible. But this is clearly not true. I mean, as all of you know, that's not a solvable position. Neither is that. Oh look, this one is. So how do we distinguish between, well, easily distinguish between corner possible orientations which are possible and which ones aren't? Well, let's see what happens if we assign each of these one distinct orientation. So, let's call clubs as one of our orientations. Would this be possible? Yes, it appears it would be. So, if this is all our first orientation, that's because if we say the clubs is worth 0, 0 plus 0 plus 0 plus 0 is 0. Let's say each of our next set of cards, so the hearts in this case, is another orientation. Let's call it plus 1. So 1 and so all of it plus 1. This is not a solvable position, as you saw, because I had to corner twist to get to it. So, why isn't this solvable? Let's add them together and see. 1 plus 1 plus 1 plus 1 gives you 4. That's not solvable. So, what happens if we take the next position? So, in this case, we'd have it all going this way around. So we have 2 plus 2 plus 2 plus 2, which gives us 8. Now, that is also not solvable. However, there are ways for you to make it solvable quite easily. Firstly, if we have it twisted like this, well, that gives us 1 plus 2 plus 0 plus 0. And this is clearly a solved position. So, 3 that time. 3 works. Now, what about, say, this position? Well, we have 2 plus 1 plus 2 plus 1, which gives us 6. And one final position to see if you can get a pattern. This one, where we have 2 plus 2 plus 1 plus 1, which also gives us 6. So, as I'm sure you've guessed by now, if the orientations here, if the number you can add it up to is divisible by 3, then it is a possible combination. So for example, the soon, 3 twisted the same way. So it is divisible by 3. So this leads to a nice consequence which tells us that if you have the first 3 cards for OLL, then the fourth set must be a specific one, so it adds up to 3. So, this set, we essentially have no more choice. We only have choice for the first 3. And if we only have a choice for the first 3, then we do 3 times 3 times 3, which would give us 27 different possibilities. Much better. Not quite perfect though. Of course these methods aren't perfect, but I think we can still do better. This is where all the orientations come in. Because the way we've counted counts this, 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 and this as separate, even though clearly they're all the same case and can all be solved by the same algorithm, at least for orientation. So, how do we get around this? The solution is the same as the last video. We just divide by 4. This won't give us a whole number, but it will take us much, much closer to the actual value. The reason it doesn't give us a whole number is cases like this, where you can rotate it in any direction, and it will still be the same number. Or cases such as this one, where this position and this position are in fact the same, but this one and this one are not counted as the same as those two. So little things like that will not hold up to scrutiny. But that gives us 6 2/3, which is a reasonable value. Reasonable-ish. It's still not quite perfect, but it will give you a much better estimate and will save you a lot of time instead of having to count every single individual case. So at this point you're probably wondering, I've been going on for a long time, what's the general way to work it out? Well, for corners, you take the number of different positions, well, the number of different corners you want to solve, take away 1, and multiply 3 by itself that many times. So we could have, if we just wanted one corner, 3 minus 1 is 0. If you multiply 3 by itself 0 times, you get 1. Say we had 2 corners. How many different positions? 3 minus 1 is times by itself once is 3. 4 different corners. 4 minus 1 times 3 is 27. Divide by 4 is 6 2/3. So, let's move on to edges now. Edges are very, very similar, but they only have 2 orientations, so I'm just going to get rid of the hearts from these sets of cards. Say we wanted to work out the number of different positions for just orienting the edges. So anything like this. Or maybe even like this. So, how many different positions could there be? Well, for this case, we want 1, 2, 3, 4 different edges. So there are 4 different orientations for the edges which you could have. So that gives us 2 times 2 times 2, but we can't count the last one because we get rid of that last card. So that leaves us with 2 times 2 times 2, 2 to the power of 3, which is 8. However, again, there are rotations which are not counted as the same. So we get 2 times 2 times 2 divided by 4, which tells us that there are more or less 2 different cases, which is not too far off. There are 3 different cases. This case, and solved. So 3 different unique cases. Our estimate gave us 2, which is not too bad an estimate. Now, as one more exercise for the just edges, let's have a look at LSE, just the orientation of LSE. How many orientation cases are there? Unique orientation cases. Well, we have 1, 2, 3, 4, 5, 6 different edges to look at. So, let's use 6 sets of cards, using just the diamond and the clubs from each of them. So, 6 different sets, but we can't use the last one because that will be dependent on the other 5. So we get 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. But as I'm sure you've realised, you can, well, there are many ways to offset it, which leaves us with 32 divided by 4, 8 unique cases. Again, pretty similar to an actual number. Now, say we had a set that we wanted to solve, which had both corners and edges in it, such as OLL, for example. It's got 4 edges in it, 4 corners. This is where orientation is nice and simple. We don't have to worry about parity or anything. We just have to find a number for the corners, find a number for the edges, and multiply them together. So, we have 4 edges. So let's move those over here. And 4 different corners. So 4 sets of 3. So, corners over here, edges over here, corners over here. How many different possibilities could there be? I'll give you a second and then we'll work it out. So, we have 2 times 2 times 2, but not the last times 2, because that's dependent on all the others. So that's 8 different edge possibilities. But of course we can divide by 4 again, so that leaves us with 2 different edge possibilities. And corners. Got 3 times 3 times 3. The last one is dependent on the others, which gives us 27. Divide by 4 again, we get 6 2/3. I'm going to round up because orientation usually gives us an underestimate. So that's 7 times 2, which gives us 14 different cases. Now that seems far too low. Where did it all go wrong? The problem here is that while yes, we can eliminate all of those corners and all of those edges, we can't always divide by 4. For example, this case is clearly not the same as, this case. Even though we did count it the same because we divided by 4 when we rotated many times. So we can't just count edges, divide by 4, corners, divide by 4. That's one too many times we divided by 4. Which means that we'll have to find some other way of doing it. But what if we found a number for this, and then a number for this, and multiply them together, without dividing by 4 first? So that would give us 8 times 27, then we divide by 4, which would give us 54 cases. Almost bang on the exact correct value. So, what we do, we find a number for this, and then a number for this. Then we multiply them together. Then we think about symmetries and mirrors. So in general, you take the number of corners you want, minus 1. The number of edges you want, minus 1. Work out the two values without thinking about rotations. And then you divide by the rotations for the whole set. So for Euler, number of corners minus 1 is 3. So 3 to the 3 is 27. Number of edges minus 1 is 3. So 2 to the 3 is 8. 27 times 8 is 108. Divide by 4. 216. Divide by 4 gives us 54. The number we want. Okay, so I hope this wasn't too confusing and helped explain how you calculate orientations on a Rubik's Cube. Next week, I'll be putting orientation and permutation together, so we see what happens there, and if there are any little tricks that we'll have to avoid in order for that to work.